Okay, so today we're going to be talking about Newman projections. I remember when I was taking organic chemistry, Newman projections were so confusing at first, but once I finally figured out an example, it made a lot more sense to me. So, first things first, what are Newman projections? Well, they're pretty much just a way to observe, like a different way to observe bonding in molecules. So, let's write that down. So it's really useful just to observe bonding, and especially when you get to really complex molecules, you get to observe how bonds rotate and the proper orientation of molecules to avoid steric hindrance and all of that good stuff. So let's do a practice example, and then I'm going to show you how to draw the Newman projection in this video, and then in the next video we will go over rotating the Newman projection, and we'll learn all about staggered and antiperiplanar, eclipsed, and gauche, and whatnot. So before I get ahead of myself, let's draw a molecule. So I'm going to keep it really simple, and then we'll do later examples that make it kind of more difficult. So my favorite thing to do when I have a line drawing is to just number my carbons. It helps me keep track of everything, so I make sure I don't lose any carbons in the process, because I feel like I do that sometimes. Anyways, so I'm going to show you guys how to draw I'm going to show you guys how to draw the Newman projection step by step, because that's the easiest way that I learned it. So let's start with carbon 2. We'll go right here. Usually when you are given a Newman projection, the question will state like to draw a Newman projection looking down on carbon 2 to carbon 3 or carbon 3 to carbon 4 and so on and so forth. In this case, we're going to draw a Newman projection looking down on carbon 2 and carbon 3, and you'll usually see an eye kind of that looks like this, okay? That just means you're looking down on carbon 2 to carbon 3. So we all know that carbon has to have 4 bonds, so right now it's just attached to 2 other carbons, and of course, the hydrogens are implied. So let's draw 1 hydrogen on a wedge and 1 hydrogen on a dash, and if you are confused with stereochemistry, don't worry, I was really confused with it too, but we will go over it in a later video, but today we're just going to focus on Newman projections, okay? So, carbon 2, back to it. This dot right here is going to signify this carbon 2, and when we're looking down on it, we see 2 hydrogens. This one right here is going to be our hydrogen that is on a wedge, and this one right here is going to be the hydrogen that is on the dash. And then finally, we have a methyl group going down. Let me just do that. So the way that I knew that this was the hydrogen that was on the wedge and this was the hydrogen that was on the dash was because if I'm looking down on it from the back side right here, that means this hydrogen is pointing towards the plane of the board, whereas this one right here is towards the back. So if I'm looking down on it from that side, then the first hydrogen I'm going to see is this hydrogen. And then this is going to be the hydrogen that's going towards the plane of the board. Next, I'm going to draw carbon 3. And we will do carbon 3 in red, the same way I have it over there. And again, the dot right here, that signifies this carbon 3. And again, we have one hydrogen on a wedge, and 1 hydrogen on a dash. Now, in this case, they're pointing towards the bottom, so we'll draw the hydrogens in. And then finally, our methyl group. And I hope you guys understand that this is the methyl group, and it's bonded the same way, just like that. This carbon to the CH3, carbon to the CH3. Finally, we can put them together. Let's just... And it's really simple to put together, I promise. So first things first, I want to show you guys that I'm going to just draw this in black right here. Carbon 2 and carbon 3 are connected through this bond, of course, okay? So let's draw them in. Here's carbon 2 with our hydrogens, and then our methyl group. And you can I'm starting with carbon 2 just because we already like it's just carbon 2, it comes first, I guess. But you could have started with carbon 3, whichever one you prefer, and it only matters that you keep one stationary when you start doing bond rotations, but we will do bond rotations in the next video, so don't even worry about that right now. I just want to show you guys how to be able to draw them because it can get kind of difficult sometimes. So now you commonly see like a circle drawn over here. This circle, this black circle, is the bond between carbon 2 and carbon 3. And now that we've drawn carbon 2, we've drawn the bond between carbon 2 and 3, we can draw in carbon 3. And again, carbon 3 looks just like this. You have a CH3, a hydrogen, and a hydrogen. Now notice that I have carbon 3 connected to this black line, not connected to this center, because this center right here is carbon 2 bonded to this and then this black line is the bond between carbon 2 to carbon 3, and then we have the substituents on carbon 3. I hope that makes sense. Now, I just want to talk to you about some terminology now. As you see, we have the two methyl groups are 180 degrees away from each other. When the two largest substituents are 180 degrees away from each other, that is the most favorable structure. Two largest substituents are 180 degrees This is called, that's the most stable, and this is called anti-periplanar. And a lot of times you're asked to draw the structure that is anti-periplanar. And in this case, this is anti-periplanar because we have the two methyl groups, which are the largest substituents, in this case, 180 degrees away from each other. And that is the most favorable because it reduces steric hindrance. Sorry, I'm just making this line longer because I feel like it looks weird. So the reason this is most favorable is because it reduces steric hindrance, which makes sense because, you know, the molecules want to be happy. They don't want to be too close to each other. They want to have their space, and that's exactly, I don't know what I just did there. They want to have their space, and that's essentially what's going on there, okay? Sorry about that. Okay, it won't let me write. I don't know what's going on. Oh, there we go. That works. Anyways, yeah, the reason anti-periplanar is the most favorable and the most stable is because it reduces steric hindrance. So the way that we just did this structure, that is a super easy and foolproof method on how to draw a Newman projection. In the next video, we will go over, I want to switch colors over here so that we can put it in something nice. Well, it doesn't seem like we have some very nice colors, so we'll go in the next video. We will go over how to rotate. Very fun, and it's a lot easier than it sounds. So I'll see you guys in the next video. Please like and subscribe to my channel for more. Thank you.